Let's take a look at an example of idler gears. Down here we have a simple two-stage gear train, which is made up of 3 gears. Now let's go ahead and label the elements of the gear train. We'll start with the ground and call it 1. And this first gear we will call 2. The next gear will be 3 and 4. And so the arm between 2 and 3 is just element 1, the ground. And same with between 3 and 4 is just the ground. We'll consider gear 2 to be our input with a speed of omega 2, and gear 4 to be our output with a speed of omega 4. And sitting in between is gear 3, which is our idler gear. And now that we have our elements labeled, we can write out the rolling contact equations so that we can see how the idler gear affects the gear ratio. We have one rolling contact between gear 2 and 3, and one rolling contact between gears 3 and 4. So we're going to have 2 rolling contact equations. The first equation is 2 rolls externally on 3 relative to arm 1. And the second equation is 3 rolls externally on 4 relative to arm 1. Hopefully that makes sense. We have this gear right here spinning in circles and it's turning, this gear right here, and they're both just pinned on the ground with like these pins right here, and they're not orbiting around each other, they're just spinning in place. And then you have gear 3 is rotating gear 4. So let's write out these rolling contact equations mathematically. So equation 1 becomes rho 2, which is the radius of gear 2, times delta theta 2, so the change in angle of 2 relative to 1, is equal to a minus, because it's external, rho 3 times delta theta 3 relative to 1. And likewise, 2 becomes rho 3 times delta theta 3 relative to 1 is equal to minus rho 4 times delta theta 4 relative to 1. So a simple substitution gives us rho 2 times delta theta 2 relative to 1 is equal to a minus rho 4 delta theta 4 relative to 1, and the minuses are obviously going to become a plus, and if we take a time derivative we get rho 2 times omega 2, the speed of gear 2, is equal to rho 4 omega 4, which is the speed of gear 4. And remember that the ground is constant, it's 0, so when we differentiate that drops out. So we could write the output speed omega 4 as a function of the input speed, which would be rho 2 over rho 4 times omega 2. Or we could write the gear ratio, which is the input speed omega 2 over the output speed omega 4, which is rho 4 over rho 2. You'll notice gear 3 does not affect the output speed of gear 4. Only the input gear, gear 2, and the output gear, gear 4, affect the value of the gear ratio. However, you'll notice the gear ratio is positive. If gear 3 were not in the gear system, the ratio would be negative, and the output gear 4 would be spinning the opposite direction of gear 2. So why do we use idler gears? Okay, the first reason we use idler gears is what we just saw, the change of rotation. If you need the output gear to spin the same direction as the input gear, you can achieve this by using an idler gear. Another reason to use idler gears is because there may be a large space between the input and the output gears. You could use a series of idler gears to bridge the gap. And lastly, the idler gear can be used to reduce the stress in the gear teeth between the input and the output gears, which can often happen when there's a large disparity in the size of the gears. Hopefully that helps you understand idler gears and you've got a really good grasp on the external rolling contact. In the next video, we're going to look at the internal rolling contact. If you found this helpful, please click the like button and don't forget, hit subscribe so you can catch all of my latest videos.